Today we're going to talk about systems of linear equations, computational aspects. First, let's review some ideas from before when we did talk about properties of systems of linear equations. Say that we have a system of m equations and n unknowns. Visibly, we can write it as follows. Here, the x1, x2 through x sub n are the variables, or are n unknowns. We'll denote S here as our system. We can write our system as a single equation, A times x equals B, once we introduce the following matrices. A, which is an m by n matrix, simply keeps track of the scalars aij. X, which is an n-dimensional vector, keeps track of the variables x1 through x sub n. And B, which are just the coefficients on the right-hand side of the equation. We can make a few definitions about this system of linear equations. We'll say that any vector S is a solution to our system if A times S equals B. The collection of solutions S will be called the solution set to this system. We'll say that our system is consistent if we can find at least one vector S such that A times S equals B. Otherwise, we'll say that our system is inconsistent. We'll say that our system is homogeneous if the right-hand side, B, equals the zero vector. That is, each of the scalars b1, b2 through b sub m are equal to 0. Otherwise, we'll say that our system is inhomogeneous. We'd like to state a few properties of such a system. Say that we have, again, a system of m equations and n unknowns. We'll denote V as the collection of vectors x, that is, f to the n, and W as m-dimensional space, f to the m. Let's denote K sub h as the solutions to the homogeneous equation A times x equals the zero vector. Then we can think of K sub h as the null space of left multiplication by A. In this case, the dimension of this subspace is n minus the rank of A. Remember that n is the number of variables in our system. Say for the moment that m is less than n. That is, that we have fewer equations than we do unknowns. Then there exists a non-zero solution S to our homogeneous equation A times x equals 0. Non-zero means that we have a vector where not all of the coordinates of the vector are 0. Let's denote K as the set of solutions to our system, capital S. For the moment, let's say that our system is consistent. That is, we have at least one solution denoted by a lowercase s sub 0. Then all solutions are the form s sub 0 plus k for some lowercase k in our set capital K sub h. Finally, let's say that m equals n. That is, we have the same number of equations as we do unknowns. Then our system has exactly one solution, s sub 0, if and only if A is an invertible matrix. Today we'd like to talk about how to practically solve such a system of equations. We'll give a motivating example to explain how we're going to do this in the future. Let's consider a system of two equations and two unknowns. We'll assume for the moment that we have the following identity. A11 times A22 minus A12 times A21 does not equal to 0. Assuming this, we'll try to find a solution S. To do so, first, we'll try to isolate the variable x1 so we can solve for it. Let's multiply the first equation by A22, multiply the second by negative A12, and then add the two equations together. You see here that we've eliminated x2 from our system, so now we have a single equation involving just x1 alone. We'll use this later to solve for x1. In a similar way, we can isolate x2. To do so, we'll multiply the first equation by negative a21, the second equation by positive a11, and then we'll add these two equations together. This time you'll notice that we eliminated x1, and now we just have a single equation involving x2. Since we have equations involving x1 and x2 alone, we can use this to actually find our solution, S0, which you see here on your screen. Let's give a different way to find the solution, but now using matrices. Recall that we can express our system of linear equations in the form A times x equals b in terms of various matrices A, x, and b. The quantity we mentioned before, A11 times A22 minus A12 times A21, is called the determinant of our 2 by 2 matrix A. We'll come back later in the course and discuss this in more detail. Remember, we had worked out before that as long as this determinant is non-zero, then we can find the inverse of this 2 by 2 matrix. Using this, we now see that our S0, our solution that we found on the previous screen, is actually equal to A inverse times B. So now we can write a very simple solution to A times x equals B as S inverse equals A inverse times B. We're going to discuss a much more general philosophy as we move throughout the course. Since we're still trying to discuss how we'll find solutions to our equations, let's now discuss the concept of Gaussian elimination. This will give us another method of finding solutions. Let's start with the definition. We'll say that a matrix is in reduced row echelon form if it satisfies all of the following conditions. First, let's take a look at the individual rows. For a given row, if it has a non-zero entry, then moving from left to right, we want the first non-zero entry to be 1. If this is the case, we will call this a pivot. The variables in our system of equations corresponding to the pivots will be called the leading variables, and the other variables will be called the free variables. We'll come back in a later course and discuss this in more detail. Next, let's look at the columns. If an individual column does contain a pivot, then all of the other entries in that column must be 0. That is, every column has exactly one non-zero element, and that non-zero element is the number 1. Third, let's take a look at the rows that contains pivots. Every row that has a pivot in the row above, that row above must have a pivot further to the left. The idea here is that what we're left with morally has to look like a diagonal matrix, or at the very least, an upper triangular matrix. There shouldn't be any non-zero entries that go down below the main diagonal. Here's some examples. We have a 4 by 4 matrix on the left, another 4 by 4 matrix in the middle, and a third on the right. Let's try to discuss what would the pivots be for these various matrices. To do so, we have to look at the matrices row by row. So let's start with the very first row. We see here, moving from left to right, that we have a non-zero entry, and this entry is a 1 for each of the matrices. So far, we're okay. Let's move to the second row. For the matrix on the left, we see that there's a problem. As we move from left to right, our first non-zero entry is a 5. This is not a number 1, so this matrix on the left cannot be in echelon form. In the middle and on the right, we see as we move from left to right in the second row, our first non-zero entry is a 1, so we're okay. The 1s here do form our pivots. Let's move to the third row. In all three cases, we see that moving from left to right, the first non-zero entry is a 1, so these are all pivots. Let's move to the fourth row. You'll see that for the examples on the left and in the middle, again we have pivots, but for the matrix on the very right, we have a row of zeros. There is no pivot here, but we're still okay, because remember that the idea is we have to look at the non-zero rows. This is a row of zeros, so there's nothing to worry about. Next, we have to check the columns. Recall that we're checking the columns that each have pivots. So for each of the matrices, let's take a look at the first column. We see here that in each of these three matrices, we do have a pivot in the upper left corner, and all of the other entries in the first column are 0. So we're okay here with the first column. Let's move to the next. Here you'll see on the left, we don't have a pivot. Remember that we had the non-zero entry 5. So in some sense, there's nothing to check here for this column. However, for the example in the middle and the example on the right, we do see that we have pivots, and we see that all of the other entries in that second column are 0. So we're okay so far. Let's move to the third column. You'll see for the example on the left, we have a problem. We have 3, then 10, then 1. The 1 was a pivot, but the 10 and the 3 above are non-zero. So again, we see that the matrix on the left is not in echelon form. However, the matrices in the middle and on the right do indeed satisfy the rules that we like. Let's move to the fourth column. In this case, the matrix on the left you see has problems. We have 4, 15, 8, and 1. The 1 is a pivot, but unfortunately we have non-zero entries above in the 4, 15, and 8. So again, we see that the matrix on the left is not in echelon form. However, the matrices in the middle and on the right are indeed so far in echelon form. You'll see that the matrix on the very, very right has a column of zeros. This is okay because this column does not contain a pivot. Let's move to the last example, to the last criteria. We must check where all of our pivots are in these matrices. Let's take a look at the matrix on the very left. We have 3 pivots in the first row, the third row, and the fourth row. The criteria here says that in the row above, the pivot must occur further to the left. If we start with row 4 and then move up to row 3, notice that the 1 goes back to column 3. And if we move up to row 1, the pivot now is in column 1. So the matrix on the left does indeed satisfy the rules that we like. Let's take a look at the matrix in the middle. We have our 4 pivots painted red. In the fourth row, we see a pivot in column 3, but in the third row, we see a pivot in column 4. Because we don't move up and to the left, we see that the middle matrix is not in echelon form. If we move to the matrix on the very right, we see that we have 3 pivots, and it looks like we have a nice upper triangular matrix, or at least in this case, a diagonal matrix. You can see that the 1s are in this very nice pattern, and this is exactly what it means to be in echelon form. Let's recall a concept so that we can make a definition. Given a matrix A, recall that there are just 3 types of elementary row operations we're allowed. Type 1 says we can interchange any 2 rows of A. Type 2 says we can multiply a row by a non-zero scalar. And type 3 says we can add a scalar multiple of one row to another row. Using this, here we introduce some methods of how to solve a system of equations. We're going to introduce a series of steps to arrive at a matrix B that is in reduced row echelon form. Step number 1. Let's start perhaps at the upper left entry. If we have zeros, then we're going to swap with the row below so that we have a non-zero entry in this first column. Again, we're swapping so that at least we have a non-zero entry to start with. This interchanging of rows is what we'll call a type 1 operation. Once we have this non-zero entry, let's divide the entire row by this non-zero number so that the entry we have now becomes a 1. This, of course, will become our pivot. This is what we call a type 2 operation because we've multiplied the entire row by a number so that we have a number of 1. For step 3, we're going to add and subtract this row from the other rows so that we have zeros in all of the other entries in this column. This will be a type 3 operation so that now not only do we have a pivot, but we've eliminated all of the other variables from this column. For step 4, now we'll move down one row and over to the right. and we'll repeat this algorithm all over again. Think of this as for steps 1, 2, and 3, we in a sense try to isolate variable x1, and then for step 4, we move on to the next variable, perhaps x2. We'll denote the matrix that we get in this form, the reduced row echelon form. This whole algorithm is called Gaussian elimination. Let's give an example of this to explain what's happening. We'll consider the following system of 2 equations and 3 unknowns. We'd like to try to solve for x, y, and z best that we can. Remember that we can express this system using a 2 by 3 matrix. Here we just want to keep track of the coefficients in front of x, y, and z. First, we'll try to isolate x. To do so, let's multiply -2 times the first equation, and then we'll add that to the second equation. Here, we've done this so that we can eliminate and just isolate x by itself. Well, this operation of adding twice the first row to the second is just the same as performing an elementary row operation. Recall that here we're just simply multiplying on the left by an elementary matrix. Next, we'd like to try our best to isolate y. So first, let's get rid of the -1 times y so we can work with it in a slightly easier way. Multiplying the second row by -1 is another type of elementary row operation. Again, we're just going to multiply on the left by an elementary matrix. Finally, we'd like to isolate y, so we're going to add -2 times the second equation to the first equation. This will now mean that we only have one equation involving x and one equation involving y. This operation of adding -2 times the second row to the first row is simply another elementary row operation. So again, we can multiply by an elementary matrix on the left. Putting all of this together, now that we've eliminated to solve for x and y, we really see that we've actually computed the reduced row echelon form of our original matrix A. This example is supposed to exemplify that one of the reasons why we perform Gaussian elimination is so that not only will we find a simple matrix when we're done, but we can also find a very simple set of equations in which we can readily solve for certain variables. I'd like to end today's lesson by discussing what are called column spaces and row spaces. First, let's start with an M by N matrix A. Recall that the transpose is what we get by simply replacing the columns of A with rows. The column space of A is that subspace generated by the columns of A. Quite literally, we take a vector and we multiply on the left times A. This gives us now a linear combination of the columns of A. This collection of linear combinations is what we call the column space. You'll notice here that we've placed in red A11, A21 through AM1 as the first column of our M by N matrix A. This is exactly what we mean by the column space. On the other hand, the row space of A is that subspace generated by the rows of A. Perhaps an easier way to see this is you can take the transpose of A and now consider the space spanned by the columns of A transpose. Here we've placed in red one of the first columns that you'll see in our space, A11, A12 through A1n. This is the first column of our matrix A transpose that you can see at the upper left of your screen. Of course, because this is the first column of A transpose, this also corresponds to the first row of A. You can see this in red at the upper right of your screen. We'll now list some key results which are not listed in the textbook. Let's say that A is an M by N matrix. We'll denote B as the reduced row echelon form of this matrix, and let's let S be the collection of pivot columns of B. Remember that these are the columns that have exactly one non-zero entry where we have a pivot and zeros everywhere else. First of all, the row spaces of A and B are the same. Second of all, this collection of pivot columns forms a basis for the range of left multiplication by B. Third, the rank of A is the rank of B, it's just the number of the elements in S. In other words, it's the same as the number of non-zero rows of B. Finally, let's say that M equals N. That is, A is a square matrix. Then A is invertible if and only if its reduced row echelon form is the N by N identity matrix. We simply like to point out that even though the row spaces of A in its reduced row echelon form are the same, this is not true for the column spaces. We'll see an example of this on a future homework assignment. Let's discuss the very first statement. Since B is the reduced row echelon form, we know that it can be constructed by a series of elementary row operations. That is, we can write B as E times A for some product of elementary matrices E. But we also see that E must be invertible because it's the product of invertible matrices. By looking at the transpose, we actually have the following diagrams. We see that we can first multiply by E transpose, then multiply by A transpose to find B transpose, or we can multiply by the inverse of E transpose, then multiply by B transpose itself to find A transpose. Using both of these arrows, we actually do see that the range of A transpose is the same as the range of multiplication by B transpose, which is just the same thing as saying that the row spaces are the same. Let's focus on the second statement. From the way that we've constructed B, we see that the range of left multiplication by B is just the span of S. Again, you'd have to stare at the way that we have the pivots that are placed. Since each row contains a unique pivot, we know that the columns are really just a collection of standard basis vectors. Remember that we have a column that has 0 entries except for exactly one non-zero entry, which is a 1. That means that the columns are by definition just collections of standard basis vectors. But because S is a subset of a linearly independent set, S itself must be a linearly independent set. But now we have a linearly independent set that spans the range, so S must indeed be a basis for the range of left multiplication by B. Now let's show the third statement. Since B, which is the reduced row echelon form of A, is simply E times A for some matrix E, then we know that the rank of A equals the rank of B. But by the definition of rank, we know that the rank of B is the dimension of the range of left multiplication by B. But we just showed that S is a basis, so the rank of B must be the number of elements in our set S. So the rank of A is just the number of pivot rows for B. Let's show the final statement. First, let's assume that the reduced row echelon form is the N by N identity matrix. Well, this here has N pivots, so the rank of A must be N. But because the rank is N, we know that A must be an invertible matrix. The pivot columns are the standard basis elements, so we see that B here must be the N by N identity matrix. Thanks for watching.